Here is an example of multi-level feedback queue. Okay, we have 3 queues. The first queue is round robin with a millisecond as time quantum. The second one is also round robin with a little bit longer time quantum, which is maybe 16 milliseconds. And the last one is the first come, first serve scheduling. Okay, the scheduling mechanism for working as follows. A new job comes, it always input into the Q0, Q0, okay, in the real of the Q0, okay. So when the Q0 job gain the CPU, it receive a millisecond, so the time counter. If it finished within a millisecond, that means a call, a system call or terminate, okay? Then it stay in Q0. If after a millisecond, the CPU burst did not complete, then that means this particular process would require a longer CPU burst time than the time quantum assigned to this particular Q result. Then this process will be preempted and downgrade to Q1. Okay. The Q0 jobs in Q0 has high priority, so we can assign a portion of CPU time for process in Q0, okay, and another portion of time for process in Q1, okay. But anyway, if a Q1 process is scheduled to use CPU, then you will always get 16 milliseconds as its time quantum. Okay, if within 16 milliseconds it finish its current CPU burst, that means okay, the CPU burst may be less than 16 milliseconds. Okay, in the future also. So this kind of process will stay in Q1. Okay. Otherwise, if 16 milliseconds is still not enough for its CPU burst, then after the time quantum expired, this process will be preempted and downgrade to the Q2. Okay, to the okay. And when the process in Q2 is scheduled, okay, to use CPU, then because the first come first service was in this queue, okay, so the process will continue to finish. Okay, so that's the a single example, and conceptually will be something like this. Okay, all the process when they enter the system, they first stay in Q0 with time quantum 8 millisecond, and if 8 millisecond is enough for its CPU burst, then it stay in there. If for some CPU burst, the 6 millisecond is not enough, then it will be preempted and downgrade to Q1 for 16 millisecond time quantum. Okay, and similar things happen if 60 millisecond is good enough for its CPU burst time, then it will stay in Q1 until it's not enough for its CPU burst. Then those processes require a longer CPU burst will be eventually downgraded to the last queue, which will be served by first come first serve. Okay. The next kind of application we are talking about will be real time. Even an application user process or process has real time requirements. Okay, And usually we mean real time means is time critical. That means when we try to execute this kind of application, the completion time or turnaround time or response time was very important, and then they have a limitation to when or how when to finish this request or whatever. Okay, so this kind of an application has this kind of requirement, or sometimes we call it time critical applications. Okay, they have some guaranteed the response time requirement. Okay, and this kind of application, okay, there's a term terminology we will use for the following discussions. Okay, a start time is the time which the task must start in response to some events. For example, when the smoke alarm detector find out there's a smoke involved, okay, then the response to this smoking detection should be the process will respond to the smoking detection should be started within a short period of time, okay, when the event happens. Okay, so that's the start time. Okay, I mean the task must start in response to some external event, such as interrupt from a sensor. Okay, the smoke detector is a kind of sensor. Okay, so that will be the some requirement. Okay, and the deadline is the time in which when the task must be complete. Okay, for example, okay. For sometimes, go back to this small detection example. Okay, sometimes the start time is not too critical, but the data maybe is more critical. Okay, so after this small detection event happen, then maybe the data will be during within 1 minute, 1 second. The alarm, okay, should be issued, generated. So all person within the building will be notified. Okay, but so not only the physical alarm, maybe if the system has the notification goes through the mobile phone, so everybody should receive this notification from the mobile phone. Okay, and also the alarm, physical alarm. Okay, and maybe there is a notification requirement may include that not only notify send them event message to all the mobile phone within this particular building. Some alarm information or not may also need to be sent to a nearby fire department also. Okay, but the data for this message delivery may be a little bit different. For example, the requirement for alarm for physical alarm may be within 1 second, and the requirement for send event notification through the mobile phone maybe within 2 seconds, and within 5 seconds the message should be sent to a local agency, okay, or fire department or relative agency, okay, government agency also. Okay, so then that's the thing. Okay, for different applications may have different data requirements. Okay, corresponding to the same events. Okay, the smoke alarm, smoke detection within in a building, for example. Okay, and the data may be we can categorize the data into two classes. One is hard data, another one is soft data. Hard data usually means, okay, if the data is missed, then the value of this information, okay, or the computation may become useless, or sometimes not use this, but some dramatic situation may happen, or okay, a disaster may happen, for example. Okay, follow the smoke detection events. Okay, if, for example, within 9 seconds or 5 seconds, the alarm should be sent to the fire department. Okay, and when the fire department receive this alarm, okay, and then a new application may be launched. For example, by the regulation, the fire department may need to be, for example, say within 5 minutes, the fire department should send out its first fire cars for emergency assistance cars, okay, or ambulance or whatever, okay, to send out, okay, and maybe within, say, for example, because those fire departments or relative local agency, they are nearby to the fighting the smoke detection event to the press will happen, detect smoke. So maybe the requirement is that we, after the receive the information, the event, okay, that those relative agencies should have their assistant persons, for example, the fireman or the ambulance, or okay, should be able to arrive in the building within 15 minutes, for example. Okay, so that's the, and this 15 minutes maybe we call it soft data, maybe, okay, but it maybe depends on the regulation. Okay, some critical one may require this as a hotline, because if the building contain some hazard materials, okay, for example, then maybe the requirement will be hotline. Okay, if it's a normal building, then maybe this requirement is the soft data, because hard data means if they cannot come within this data, then it becomes useless, because then the building may be exposed, because if the building contains some explosive materials, okay, so then after detect this smoke or even fires, okay, then within this particular day, the data, then the building, the explosive may explode, okay. So depends on the situation of this event, okay, and the requirement. Some the data are hard, okay. Some maybe soft, okay. Soft data means if the process, the computation, okay, or the handling this the application require more time or finished, not within the data, but a little bit delayed. It's still useful, but the value of the process may become decreased. Okay, so that's the sub real time or sub data means. Okay, the meaning is semantics of this. Okay, so real time application usually content have this time requirement. Some may have start time requirement. Some may have data requirement, and the data may be hard or soft. Okay, a real-time system is that this system can guarantee the real-time applications running in this system have this time critical data supported. Okay, that's the system. And how real-time system usually they can guarantee all the tasks running in the system. They can meet their hard deadlines. Okay, and some real-time system usually provide this time guarantee using the best effort. Okay, so not all the applications in the system meet their deadline, but the system will try to guarantee most of them. Okay, and the real-time operating system usually they to guarantee this time requirement, they usually use priority scheduler. Okay, because depends on the deadline for each applications. Okay, some may the highest priority usually means they have a much critical requirement for the time. Okay, and for this kind of operating system, usually interrupt services they all require guaranteed maximum service time. Okay, so in parallel, those services be deployed to the system. The maximum time requirement for each service should be recorded and be known prior. So when the event happens, the system know how to schedule, how to guarantee that all the services be handled within the time requirement. Okay? And also memory management and multi-thread execution or preemptible systems, they all need to be considered or supported, because a more critical application comes in, usually give the system will give it a higher priority. So to guarantee this high priority job finish within its daytime, the preemption may it become required. Okay, if the system did not support preemption, then there's no way to make sure that the high priority job or the time critical jobs they can meet their deadlines. Okay, so real time process usually they are loaded into the system's memory, okay, before those tasks can start to execute. Okay, otherwise, so some kind of the virtual memory management usually will not be applied to real-time application processes. Okay, and the normal process usually we may use virtual memory management. This management mechanism we will discuss later. Okay, but for real-time processes, usually they need to be loaded into the memory as a whole. Okay, you cannot use in any virtual memory requirement. Okay, otherwise it's very possible the data will be violated. A task may be a terminating process which run and then exit. Okay, so its data will be the latest time that it must exit. Okay, so this kind of task we call it a periodic task. So it just happened once, or when the event happens, when the related event happens, then the task will be executed. Okay, so it's one shot or event-driven task. Okay, and the task may be non-terminating process. That means in general it may be run for a long time, but perform periodical operations. So that means periodically this task would be triggered to run. Okay, for example, time interrupt, the time quantum time interrupt. Okay, for the scheduling. Okay, so whenever you schedule a new process to use CPU, you set time content. And time interrupt periodically. So the time interrupt handling routine will become this non-terminating process because it will not really terminate, because periodically you will be triggered and withdraw, then will be executed. Okay. And another example is this audio video encoder and decoder. Okay, so when you your computer you using this audio streaming service or player or video player. Okay, the encoding and decoding is mixed with the rendering and display mechanism. Okay, so you get a file, it encode a portion of the video stream, and then send out. Okay, so that's for the network, the video streaming. Okay, the center part, they periodically they encode the image frames that received, okay, captured from some camera or whatever. Okay, then send out through the network, and the receiver side, they after receive a portion of the or frames or images, they will decode, okay, according to the corresponding decoder, and then after decoding, they will send to the display to render to display. Okay, and periodically this decoder will be triggered to decode the undecoded image frames, and so on. So that will be more or less a non-terminating process, or we call it a periodically task. Okay, so periodically this task will be triggered to execute. Okay, so its daytime is not the time to exit. Okay, because the daytime is periodically, so every period you have a daytime. Okay, but rather the time by which result have to be ready for each period of execution. Okay, so for example, the period may be 10 milliseconds. So every 10 milliseconds, this decoder will be triggered to decode those received. Okay, during the previous period. Okay. So so the system may can and after you and then there's you have a data. Okay, the decoder after decode, they can then they will receive the incoming frames. Okay, so every 10 milliseconds, for example, the period will be set to 10 milliseconds. Then the first 3 milliseconds is decoding the previous period, the recorded the strings, and then the previous period received the images can be decoded within 3 milliseconds. Then the next 7 milliseconds, the process can be used to receive incoming frames. Okay, and so on. Okay, so maybe this decoding video player, okay, will contain several tasks. One is the decoding, one is the play task. Okay, and they all have same 10 millisecond period. Okay, but they have different deadlines. Okay, for decoder application, maybe the data will be 3 milliseconds. Within the first 3 milliseconds, they need to be finished, and the player, maybe the data for the display part will be maybe say within 10 milliseconds. Okay, at the end of the period. Okay, so So the operation, the system have these two periodic tasks, and then they in every 10 millisecond time slots. Okay, and the scheduler should be able to schedule that the decoder should run first, and then followed by the player, okay, within each period. And then so the next period, these two applications, if they all schedule in a way that the decoder run first, and then followed by the display. Okay, so the overall will generate a very smooth video play scenario. Okay, and so on. Okay. And computing time will be the time to perform each periodical task. Okay. Data will be the time that each periodical result must be ready. So, for example, we said it before, a video player may contain two periodical real-time tasks. One is the decoder, another one is the display. Okay, they all have the same period, 10, and the computed time, for example, the decoder maybe 2 milliseconds, and the display maybe 5 milliseconds. Okay, and the data for the decoder maybe say 4, and the data for the display maybe in 9. Okay, every within the period of the 10, the display should be finished before 9. So then the users can be able to go through the video stream very smoothly, because every 10 milliseconds they receive the required frames to show up in these 10 milliseconds, for example. Okay. So here is a typical example. If the period is T, and D will be the daylight of the task, these periodical tasks. C is the computing time, I mean the real processing time, CPU time required to perform the task. Okay, then the timing required to perform the task, C, must be less than or equal to D. Okay, otherwise it's impossible to finish to meet the data. Okay, and the data must be less than or equal to the time period. Okay, so for a periodic real-time task, okay, these three time requirements will have this inequality relationship, inequality relationships. Okay, to schedule this periodical real-time tasks, okay, or schedule real-time tasks. Okay, there are two major scheduling policies. The first one is earliest daytime first. Okay, that means for each real-time process, okay, it will tell the operation system is daylight. Okay, or next daylight if it is a periodic task. Okay? If it is a non-periodic task, a periodic task, then it's daylight. If it's a periodic task, then it's the next daylight. Okay, and the schedule will pick the process that has the nearest daylight to run. Okay, so the daylight, which one has the shorter daylight starting from the current time. Okay, the daylight will meet. Then the also earliest daylight will get the run to first, have the highest priority. Okay. And in general, a process can run to completion if it has an earlier daylight. Okay. But because real-time system usually use preemptive and priority, so if there's during the execution of this current task, if a new task comes arrive and with shorter data, with earlier data, then the running process may be preempted. So the task which just arrived with early data, where we get the CPU. Okay. The next popular schedule is this select first. Okay. The select means the time remaining for the completion time and the data. Okay. The difference between the data and the computing time. Because sometimes the data, if the computing time required for a process is larger than its next data, then if we schedule this process, it cannot meet its data. Okay, so we not only consider that, but we also consider how much a process can be delayed. Okay, the select means the time to data, the current time to the data, okay, to its next data, the remaining minus the computing time, remaining computation time, because a process a task may be run a portion and then preempted. So you have a remaining computation. Okay. So the current time to data, the time required from the current time to the data, minus the remaining computation. That's the stack time of a particular task. Okay. So this stack time first means, okay, you always let those process which if it did not start right away, okay, it's a small stack time, then first. So that means you delay a task until it is necessary. Otherwise, the task will violate the data. Okay. So, for example, suppose the computer time is 5 minutes second, and T is 20 milliseconds from now. Then the stack will be 15 milliseconds. So that means this particular process can be delayed 15 milliseconds, and then start to not. It's still meet the data. Okay, so the stack, this stack first, that means we always run those execute those tasks which has smallest stack. So that means if you delay this process, then this has a high possibility to violate its deadlines. Okay. So consider that. Okay. Now we will compare this select first and earliest data first. Okay. The characteristic of these two algorithms. Right? For earliest data first, that means the data earliest one always finish before others. Okay. And this select first can get a more fair result. Okay, so that means if some for early data, the data, the early data they get free. So those processes which has early data they can finish. Okay, and the other process they have longer deadlines may not be when the time try to run and the time may be not enough to finish, okay, before their deadline. Okay, so you can see that those with more far away deadlines, the possibility of them did not meet their deadline become higher. Okay, and for this stack first, that means the possibility for all the process to violate their deadline it's not only depends on their deadline, okay, but also depends on how much time is required to compute to perform the task. Okay, so so in general, this slack time first can get more fair result. So it not always guarantee some of the tasks. For example, if all these tasks are periodic, okay, and those they have a not earlier than none task, okay, within the period, they can always they always guaranteed because they are running first, okay. But for those they not it's not so critical. Then the opportunity, the possibility that they denominator will become higher. So the possibility or probability to not meet the data for different tasks are different. Okay, so in some sense it's not fair. But for the Slack first, okay, because they consider the computing time also. Okay, that means if a task which although their deadline is later, but if those tasks they require more computing time, then maybe those tasks can get executed first, okay, because the remaining stack is small, okay. So it's possible for those data is far away, they can still get an opportunity to complete. Okay, not every period those only those earlier data tasks can be completed. Okay, by using step first. This step first is possible. Some of the process which, although their data is not too early, okay, it's very close to the period, end of the period, they can still get served. Okay, and a different period may be different. Okay, and so on. Okay. So the difference to data can be balanced if there are not enough time for everything. Okay. If the resource is enough, all the process can meet their deadline. Then these two make no difference. The earliest deadline first can get all the tasks finished before their deadline. Or the compute, if for example a set of process that their compute time, summation of their compute time is smaller than the period, then early data can guarantee that everybody will meet their okay. It's possible to meet their requirement. Okay. It's like this record also possible to meet their requirement. Okay. But if the resource is not enough, then early data only some early data process may finish. But in this step first, all the process have the equal possibility to meet their deadline, okay, to violate or defer, okay, or did not meet their deadline, okay, but they may all missed, but roughly by the same amount, okay. in the situation that some of them may finish, but it's not earlier. Only those early deadline processes. Okay, some process which later deadline can still finished, or if nobody can finish, then everybody miss their deadline by a certain amount of time is possible. Okay, so for this slack time first. Now we will go discuss a very famous real-time scheduling policy we call rate monotonic scheduling. Okay, we only consider periodical tasks. Okay, if there's a static set of periodical tasks, okay, and these periodic tests, they can be the schedule is priority schedule. Okay, then we can assign a static priority to every task according to their period. Okay, highest frequency, or sometimes, in other words, the period is smaller, process get the highest priority. Okay, the lower frequency process, that means that their period is longer, get lower priority. Okay, and all periodic real-time process have the period known in advance. Okay, and are running at the same time, starting at the same time. Okay, then you can schedule this periodic real-time task by using the simple priority schedule. We call it rate monotonic. That means the rate higher, okay, a smaller period, then you get a higher priority. Okay, if two processes have the same priority, then they can run robin. The round robin can be used for both, for those same priority processes. Okay, and rate monotonic, in some sense, is optimal. Okay, that means here the optimal. That means if it's possible, all the data can be met. That means the resource is big enough. Then the monotonic always can schedule by using the monotonic scheduling. All the process can guarantee to meet their deadlines. Okay, if the resource are big enough, okay, that is possible. Then the problem of always find principal scheduling for this set of process. Okay, so in the sense, and this was proposed by this from these papers. Okay? The detail you can find from this paper. Here we use this simple example to demonstrate this rate monotonic example. Okay, assume we have three processes. Okay, and their process ABC, their period is different. A and B has a period of 50 milliseconds. C has period of 30 milliseconds. Okay, and the 20 minutes is their computing time. Okay, 20 for A and 10 minutes for B and C. Okay, by using rate monotonic means the C should be have higher priority, and AB will be the same priority. Okay, the table of Gantt chart in the middle, in the upper half, is the scheduler, which is not using rate monotonic priority assignment. Okay, then for example, they use according to ABC, A start schedule first, and then B followed by C. Okay, then you can see that if they all started in the same time, okay, time 0. So because A to cut 20 milliseconds, so after 20 minutes, B was scheduled for 10 milliseconds, and then C missed its first period because C must be run every 30 milliseconds, but the first 30 milliseconds was assigned to A and B, so A will miss the first period, and then C got served by the second period. Okay, and after from 50 to 100, okay, the A will be scheduled again, and then B, okay, and C. Okay, so the second and third period of C is satisfied. Okay, and the first and second of A and B are satisfied. Okay, so that will be the non-monotonic. However, if we schedule C first and followed by A and B, okay, and A and B are running using round robin. Okay, round robin means you can enter. Okay, so the button Gantt chart will be based on rate monotonic. So C will schedule first. Okay, and then B and A. Okay, and B, you can see B only require 10 milliseconds. Okay, yeah. And then C and then A. Okay, and you can find out that in the first period of C, it's satisfied. Okay, and then because after I finish it, we go back to the C because she started its next period. Okay, and because C has higher priority, so A will be preempted. Although A did not finish it, but they only perform 10 milliseconds of computation. Okay, but because she require she when she comes in enter she's next period, the second period of C, so C will preempt A. Okay, so we got the 30 to 40 milliseconds will be scheduled to C, and then because A was preemptive, so this time A get served the remaining time. Okay, because in the first period of A is not finished yet, but B already finished its task within its B's first period. Okay, that's within 50 milliseconds. So and then A gets served. Okay, now we enter the next period of B and C. Okay, now, you run B first. So after B finished, we go to the 6. Okay, and then C comes in for its third period. So C is higher, so she get CPU, and then followed by A. Okay, because B, the second period B already finished. So after C finished, the only process needed, okay, still required to run will be A for its second period. So then we get now C enter its fourth period. Okay, for the so for this schedule you can see that ABC all meet their deadlines for their periods. Okay. Okay, we'll stop here for